Here we go. All right. Let's kind of see where we're at. Okay. So, oh yeah, so we were doing exponentials, and where we left off yesterday was in that rule of trying to get the same base. You had exponential equations, and so what you're trying to do is get the same base on each side of the equal sign, because once you get the same base on each side of the equal sign, you can set the exponents equal to each other. So that was 6.1. Here in 6.2 with exponential models, essentially what you can think of, these are functions that we're dealing with. And so here is an example, and a lot of what you'll see, well, a famous example are population models. You ever wonder, how do they know how many people are on the planet? I mean, they say what, 7 billion? I forget what they say now. But how do they know? How do they know? How can they predict? Well, it's a mathematical model, meaning a formula, just like this. So, and they're exponential too, in the sense that, um, hold on just a second. It's going to lighten up my emails. Oh, uh, they're exponential too, in the sense that, as you get more people, you start, kind of increasing a lot. The funny thing is, I don't know if y'all have been watching the news on this the last couple of years, but uh, the world population is going to start declining. Per the mathematical models, it's going to start declining in about what, 2070. I mean, it'll plateau and then it'll come back down. Even China is going right now, is no longer the most populous country. India took over as the most populous country. So, and both the United States and uh, China, Europe, they're all going through population declines, which is going to make Social Security, Medicare, all that stuff, kind of really bad news in about 10 years. Anywho, and a lot of that has to do with birth rates. Birth rates are way down and whatnot, and that's how they get all these models and whatnot. Is they look at birth rates and sort of extrapolate based upon that. Anywho, probably more than what you needed or wanted. So what do we have here is, we have the population of certain inner city area, whatever one, is estimated to be declining according to this specific model. And when we say model, it is a function. And notice where the variable is. The variable is located inside the exponent. Where t represents the number of years from the present, from today, so going forward. What does the model predict the population will be in 3 years? Now, you'll see that the t is located in the exponent, but look at what the base is. Look at what the base is. You see that it's the letter E. The letter E. That's what the base is on that exponent. So this is e to some power, e to the t, if you will. What is this letter E? What is this letter E? This letter E is called the natural number. I can't type. The natural number. The natural number. And it's approximately, let me see. You can do it on your calculator. Let me see. Well, my calculator updated and I can't find it as easy anymore. Scientific. So the natural number is approximately, E, the value of E is approximately, well, let me say it this way. 2 e to the first power. E to the first power is approximately 2, it's really long, 7, 1, 8, 3. That's pretty sufficient for our purposes. So if you want to use that number, 2.7183, you can use that. E is kind of like the value of pi. It's a symbol that represents a famous number, in pi, just for your purposes, is 3.141592. Okay, so you need to memorize that? No, you don't need to, but the point is it's the same sort of thing as what pi is. It represents this long decimal number. And if you use this long decimal number instead of E, that's fine. But you do, if you look on your calculator, if you have a scientific calculator, if you have an iPhone, you have a scientific calculator, you'll see there's a feature on there that says E to the x. Ugh. You'll see on your calculator it says e to the x. That's the e we're talking about here. That's the e we're talking about here. So how would you do, let's suppose we wanted to do a calculation of e squared, okay? How would you type it on your calculator? You would first hit on your calculator, on the scientific calculator, you would hit 2, and then you hit that e to the x button. Your calculator will understand that what you're trying to find is e squared. And so give that a shot real quick on your calculator. Yeah, e squared, so 7.38. So that's how you're going to do the calculation for e squared or e to whatever you want. So how would we do this one here? This one asks us, t represents the number of years, and it's telling us 3 years. So it essentially wants to what? We want to calculate what is p to the 3, p of 3. Take t and replace it with 3. So we get 572,000 e to the negative 0.021 times 3. Okay. So from here, what do we do? Order of operations. PEMDAS. Order of operations. So what does PEMDAS say? Well, we don't have any parentheses, or we do, but there's nothing to do in the parentheses, so we just skip it, okay? After the parentheses, you have to do the exponent. So we have to resolve this part of it first. Resolve that part of it first, the multiplication that's up in the parentheses. So when we do that, we get 572,000. Oops. E to the what? Negative 0.063. Now you got to get your calculator. So type in negative, where's that? 0.063, where's negative?
How do you get to a scientific calculator on an iPhone? Mine is just a regular calculator.
Did you do the update?
I mean, I'm pretty sure like it did it.
If you didn't do the update, open your calculator and turn it to the side.
Okay, and then do what?
Turn it to the side, long ways, like this.
Oh, like this?
Yeah.
Oh, I got it. Okay, perfect.
If you
Thanks.
did the update, it's a little different.
Okay.
So let's see. Oops. 0.063. Where's negative? Tell me negative.
So we're gonna put the number 2 in there first and then hit E?
Yes. Yeah, if you're doing that e squared, yes.
Well, the problem we're doing right now.
Well, you need to do that. You need to put this in. Negative 0.063. So where are we at? Oh, I did it wrong. So so if you do 0 minus 0.063, you'll get, okay, negative 0.63. Now hit your e to the x button. Oop. Well, that's strange.
It's a big old long number, 0.9389 and a bunch more numbers. Is that right?
0.9, let's see. Oh, sorry, hold on. Frustrating. Basic. Got it. Now, scientific. Oh. It won't let me do a negative number. I don't know why. Oh, now I see. Okay. I'm completely missing it. E to the x. There we go. So you should hear for this part here. So this part here, e to that turns into 0.9389. Did you get that?
Yeah, so we only have to, or do we keep on writing the whole number?
Now, 5 decimal places is good enough.
5 decimals, okay.
So then that's 572,000 times that now. And so what do we get? So times. So the answer I get 537,705, or round up 7.6. Is this what y'all got to?
5370, yeah.
Okay, good. So that's how you do it. It's just this one just says plug in the value of t and do your work on the calculator. Do your work on the calculator. The key though is how do you type it into your calculator? E is a special number like pi. You gotta be able to work the calculator. So any questions on this one? And when you go to round, you know, do you have to take the big long decimal? No, but you want to carry enough decimals that you don't lose something. If you round too much, you're going to get your answer. You'll do it right, but let's say I'll get 537,075 and you'll get 537,076. It could be a little difference if you round too much. It could create a difference. So take it out about 5 or 6 decimal spots, and you should be good. That's sort of the key. Okay, so that's how these are. A lot of these are going to work. So let's see. Same thing. It's no problem. So statistics show that the fractional part of a pair of flashlight batteries, P, that is still good after T hours, is P equals 4 to the negative 0.2 T power. What fractional part of the battery is still good after 150 hours of use? Express your answer as a decimal. So T is the number of hours. Plug in T. So same thing. P equals 4 to the negative 0.02. Now plug in what? 150 for T, because it's the number of hours. The number of hours. So this is 4 to the negative third power. Oh, well, that's not bad. We could do that. We can do that by hand. Yeah. So you could do that on your calculator too, by the way, 4 to the negative 3. So try it out on your calculator. It's the same way. But this one, if you wanted to do it on your calculator, you would hit 4. Um, then there's a key on there that says X, Y. There's a button that says X to the Y. Then hit negative 3. So let's see. 4. Yep. And so you should get P is 0. It says round to the 6 decimal places. Okay, so 0, 1. It says 6 decimal places right there. 0, 1, 5, 6, 2, 5. All of them. It's all of them. That's the answer. So you can do it this way on your calculator, or you could do what? 4 to the negative third is what? 1 over 4 to the third, which is 1 over 64, and then do 1 over 64. So there's another way to calculate it that we already know. But this is good to practice calculator work too. And so this one really is just working your calculator. That's the whole thing with this one. Okay, so another one, a cost function. You got this function here, C of t is C naught plus times 1 plus r to the t power models the rising cost of production based upon the cost today, subject to an average yearly inflation of r for over 2 years. So in other words, you got a cost today. What's the cost in a couple years, given that you have a particular inflation rate, which is kind of timely. By the way, this model here is really the same thing as the compounded interest formula. It's really the same. Not that that means anything. So what do we have here? This C, we call this C naught. zero, naught zeros, like the noughts of the 2000s. Naught is zero. That's saying that's the beginning point, the beginning value. R is the rate of inflation percentage wise, and T is the time in years, the time in years. So that's really the key with a lot of these problems is you have to understand what do the variables represent. They're telling you, but you just have to sort of parse out the information. So they're saying if the average rate of inflation over the next 8 years, T, is assumed to be 1.5% R, what will the inflation adjusted cost of a $33,000 car, C naught, be in 8 years? So that's what you have to do. You have to understand what do the variables represent and then where do all the values go. So essentially what they want you to do is calculate C of 8. C of 8. And so you plug in your C naught value of 33,400. 1 plus R. Now this has to be turned into a decimal. You can't do calculations with percentages. And then all of that raised to the 8th power. So PEMDAS, do the parentheses first. So that's 1.015, yep, to the 8th power. So 1.015 to the, so that's the XY 8 power. Oh, let me do this. Let me start typing because it's going to take a while and my handwriting's terrible. So 33,400 times 1.126493, 6 decimal places. So then times it by 33,400 and we get 37,624. Okay. And so what is this telling you is something that costs $33,400 today because of inflation in 8 years will cost about 37,600 bucks. Same item, just a higher cost. And that's kind of what we've been dealing with inflation, isn't it? Your costs today are rapidly sort of rising tomorrow. And this is a formula that they sort of use to get there. And so you can, by the way, you can use this formula if you want to figure out and see what inflation does to your dollar. Take something today, take a new computer today, $1,000 computer, and plug in today's inflation rate for R, and you'll see what does your computer today cost you in like 5 years, whatever. It's also the same sort of formula to help you understand, hey, back in the old days, I could buy a Coke for a nickel. Why does it cost $2 today or $2.50 now? Inflation. So it's the same formula. Anywho. Okay. So it
What
looks
is
like it's just really more of the same using these formulas. It's accounting. It's sorry, a lot of calculator work. Um, okay. So here you want to look at the I think what you need. Let me see. Question number 4 here says Hattie recently inherited 6,500 bucks, which she wants to deposit into a savings account. Good for Hattie. She determined that her two best bets are an account that compounds semi-annually, yes, at an annual rate of 3.3%, and a second account that compounds annually at a rate of 3.6. Which one yields more interest? What you have to know is the compounded interest formula. So the compounded interest formula is oops, A, the amount, the future amount, P, the amount of principal that you're doing today, times 1 plus the interest rate, R, divided by the number of times it compounds. Oh, wait, that's N. N. Raised to the N times T power. So in account one, what do the values represent? In account one, what do we have? P is 6,500. That's the amount we're investing. R is the interest rate, so 3.3%, which is 0.33. N It's compounded semi-annually. So what does that mean? Interest is accrued semi-annually or twice a year. Twice a year. So you compound interest in, say, the end of June, and you throw the interest into the principal and then calculate it again at the end of the year. And T is, so in this one, you assume you're just doing it on a 1 year basis. You're seeing, what do I have at the end of the year? What do I have at the end of the year? So T is 1. Okay. In account 2, it's still the same $6,500 we're putting in. The interest rate is different. It's 3.6%. The compounding is also different because it's annually, meaning once per year, and the T is still after 1 year. So which one yields more? So that you use this formula in both scenarios to see which one will yield more. It's kind of an interesting question.
I did have a question. I'm not on this one yet, but the other one, what did the CO stand for?
The starting value of the cost, the original
Okay.
cost.
Okay. Starting value of the cost.
Also, um, with the 3.3% and the 3.6%, how did we how did we sort of like convert the decimals to 0.033 and 0.036?
Oh,
Like,
yeah.
why?
So to convert a decimal to, I'm sorry, a percent to a decimal, to convert a percent to a decimal,
Okay,
divide
that's
it by
right.
100%.
Got it. Okay. Sorry about that.
Oh, you're good.
Thank you.
I just assumed I assumed it. I'm sorry. I shouldn't have assumed it.
No, totally fine. I should have known that. Thank you.
0.033 divided by 2 plus 1, yes, raised to the second power. Good. Oh, that's interesting. Okay, so now I know the answer. Interesting. So, oh, I see. Yeah. So, okay, that's the way it works. So, anyways, by the way, the answer is going to be account 2. And under this scenario, the answer is going to be account 2. Just I'll give you the answer and do the calculation. So what we see here is it's just a lot of calculator work. You have to know the formula. So that's why went through that to tell you the formula. Let's see. Joe hopes to earn $600 in interest in 2.6 years from 40,000. To decide if it's feasible to do this by investing in an account that compounds semi-annually, he needs to determine the annual interest rate. Okay. So this one here uses the same formula. A equals P okay, so P1 plus R over N to the N times T power. Now the thing is they're telling you the interest rate. The interest rate and the time. I'm sorry, they're telling you the interest and the time. So if I start with 48,000 bucks and I want to accrue $600 in interest, what's my final amount? Well, the amount you started with, 48,000, plus your interest, bring them together, means that your A value here is 48,600. It's the amount that you get after accruing interest, okay? And your original starting amount is 48,000 bucks. What's your interest rate? We don't know. That's what we have to find out. The N is the number of times it compounds, and they tell us it's semi-annual. And they want us to do it over 2.6 years. So we do 2 times 2.6. So you'll see here we have to solve for R. We have to get this guy out of there. Get this guy out of there. Ugh. Can we take the... Yes. Okay, so this is a decent one. Okay, so what we need to do is what? Well, we need to unlock that. We need to undo everything that's going on. So we need to get rid of this 48,000. How are we going to get rid of 48,000? Well, keep in mind, it's 48,000 times all this other stuff. So we have to undo multiplication, which means we have to do division. So you divide both sides by your 48,000. 48,000, okay? To get rid of the 48,000. That's the first thing. So I'm going to do that. I'm going to run out of room real quick. So I'm going to have to delete it. So when I do that, 48,600 divided by 48,000, 1 point, yep. So you get 1.0125 equals 1 plus whatever our interest rate is over 2 to the 2.6 power. Now we can resolve that. We can do that multiplication. That would be 5.2. Now here's where it gets tricky. We have to undo that 5.2, that exponent of 5.2. So how are we going to do it? This is what makes it weird. You have to take, remember, when you square something, to undo it, you do what? The square root. When you're cubing something, to undo it, you do the cube root. Whatever the exponent is the root of the radical that you need, okay? Square root, square root, cube root, all that jazz. Cool? Whatever the exponent is, that's the root of the radical. So our exponent is 5.2. That's going to be the root of the radical that we take. So we're going to do a radical here of the 5.2 root. It's weird. Okay, of the right-hand side, and that's going to cancel out this exponent right here, because we're going to do the 5.2 root on that side too. Whatever the exponent is, that's the root of the radical that you take. So we just have 1 plus r over 2 now. So the question is how in the world are we going to calculate that thing? Well, on your calculator, type in 1.0125, and there's a feature, there's a button on there. There's a button on there that has y sitting on the ledge of an x. Okay? That's the one you want. That's the root. So let me see if it gives me, oh, yep. So hit the 1.0125, hit that y sitting on the ledge of the x, and then 5.2. Yep. That's the key to the whole thing. And so when we do that, we get 1.0023918 equals 1 plus r over 2.
What do we hit after we hit the y sitting on the edge of the x?
The root, 5.2.
5.2.
Mm-hmm. Okay. Now, exponent's done. We can solve for r. We subtract from 1 from both sides. So this becomes 0.023918 equals r over 2. Multiply both sides by 2. And here we go. So 0.00478, that's fine. 2 decimal places is fine now. It was 78. And so this means that the interest rate, converting it back to an interest rate, multiplied by 100 gives us 4.2. 0.478% or 0.48%. That's the answer. That right there.
0.0478 equals R equals greater than 0.48%. Do we have to put R period?
No, that just it added a period for me
Okay. I
to
just want
find
to
it.
make sure because I
Yeah.
know it's,
Yep. There we go. So let's see. I'm going to check my answer. I'm going to put in that R now. So 1 plus 0.00. Yep, works. Okay, good. Answer checks out. So we got it. It's tough. It's tough. These are tough. A lot of calculator work, but this is essentially what we're trying to do. Is you have to do the calculator, and so you just have to know how to do it. If this was a lesson you'd skip, this if there's a lesson you need to skip, this is a good candidate. Is what I'm trying to say. It's worth only 10 points. It may not be worth it to you to go through this because it's really you're having to learn how to type everything on your calculator. That's really what this whole lesson is boiling down to. But didn't want to not do it since you're gonna. Some of y'all may encounter this, but if you're feeling good about your calculator, I encourage you to do it. It's fun. They're somewhat fun. They're interesting problems. But let's go ahead and push then to logarithms because looking at logarithms, this is actually how there's that variable being in an exponent. So sometimes we learned one way how to solve it, get the bases to be the same, and then the exponents are the same. Sometimes you can't have that. And the way that you're going to get that exponent out is by taking what we call the logarithm. It's the inverse of it. By the way, where would you use the logarithm or where do you encounter the logarithm? In your life, you probably will never use the logarithm, but it's not to say that you don't encounter it. You do encounter it. Anybody ever hear, the Richter scale and earthquakes? Oh, that was something, a magnitude 7 or 8 on the Richter scale. You remember that? The Richter scale is a logarithmic scale, and and the reason why we do a log is because it takes something that's very big and squashes it down into something small. And the reason for that is it makes it easier to see things on a graph. The Richter scale is a famous example of the use of a logarithm. So the difference between a, a 7 on the Richter scale and an 8 on the Richter scale doesn't look like much movement, does it? 7 to 8, oh, that's not big. But the magnitude, that's a magnitude of 10 difference. So a an earthquake that is magnitude 7, or I'm sorry, an earthquake that is magnitude 8 is 10 times stronger than an earthquake of magnitude 7. So it's not just a little bit more. It's a whole lot more damage than what you can experience. And so think about now magnitude 9. A magnitude 9 earthquake is 100 times stronger than a 7 because it's two spots. Okay, 10 times each time, 10 times. So that's not 10 more, but 10 times. So if you experience, think of it this way. If you want to, it's kind of morbid, but one person, 10 people died on a 7. 10 times that you expect 100 people, 10 times that 1,000 people. So just kind of think of the damage multiplies by 10. It's a lot. Anyway, so that's a famous example. So that's where we're going to see the logarithms. And it is logarithms are the inverse of exponentials, the inverse. So they're the opposites, if you will. So we'll go through a couple of these. And here's a great example. Here's a great example. I'm getting an alarm. So write the following in logarithmic terms. Okay, so what they want you to do is to be able to take an exponential expression like this and turn it into something that has a log in it. And that's what we mean, log, L-O-G, log. That's the name of it is actually the name of the operation and function as well. So how are we going to do that? Well, there's a transformation that we do. So b to the x power equals, I don't know, n. I mean, we could pick anything. N, P, Q, I'll just pick n. So this is how it's written. B to the x power, the base to the x power equals n. We can rewrite this. We can shift this around by saying log of base b of n equals x. Equals x. And it's really just, excuse me, all about orientation. Orientation, okay? So this is the transformation that we're going to use here. So you have to just identify the parts. Identify the parts. So translate it, associate it. Our b is b, so we're saying here the b is the b part. The x is the what? Is what value? What value is being used for x?
The 5.
The 5. Okay. And the n part is the
3.1.
3.1. So let's turn it into a log. Log b. Well, here's our b. It's the same. It happens to just be b. Okay. It's not always b. Our n part, our n component is the 3.1. And our x part on the other side is 5. Okay, yeah, I got it right. It's just matching up the parts and putting it in the translation. So let me give you another one. I'm going to make this one up just wholly different. So I don't like the b. I don't like the b.
And that was it?
That was it. That's
What
all.
was the answer?
Oh, so log. Oh, I don't like me to use log. Let me get the keypad. So we got to find log. Where is it?
Oh, to the left. The last line all the way to
There
the
it
left.
is. Log. And so notice it gives you a little subscript. The b is a subscript. It goes down below. That's the base. The n goes in here, 3.1. And then over here, we put the exponent of 5. So let's see. So that's the answer.
Okay.
All right. So let's do another one. And I'm going to make up something completely different. Suppose I have 2 to the x equals 32. How would I write it as a log? Remember, so our transformation is b to the x equals n. We transform it to log base b of n equals x. So this one becomes what? Well, this is our b, this is our x, and this is our n. That's kind of how I do it, is I just write over the numbers. So log base 2 of 32 equals x. You just match up the parts. Now, this thing here, the 32 is not an exponent of the 2. Not an exponent. The 2 is a subscript that's sitting below the g, and the 32 is up high. It looks like a subscript, but they are not. There's not. I'm sorry. It looks like an exponent, but it's not. It's not an exponent. You want to do one more of these? Okay. You're gonna do this one on your own. Suppose I have 4. I'll use 3. 4 to the third equals 64. Write this as a log. What's your base? What's your number? Well, let me do this. What's the base? What's the number? And what's the x? Okay, so we have log. What's the base b?
4,
4. What's the n?
64
64. Good. And the
equals
x
3.
equals 3. Good. Just matching up the parts. Feel good?
Yeah, so okay, so I understand what you're saying, but one of the first things, I don't know if it's still on there. I know. You had said B with the X exponent equals N. What was that for?
Well, that's the start. That's okay. So that's what we call the exponential form.
Okay,
Okay.
that's exponential form.
This is what we call exponential form. Why? Because it has an exponent. There's one part of it has an exponent. And what we're saying is this is a transformation. You can transform it into a log expression by way of this manipulation.
Okay.
Because sometimes it's helpful to do. You'll see in a moment why it's helpful to do.
Okay.
We can go in reverse too. I can give you a log expression. Um, I can give you a log expression too. Log base 2 of 8 equals x. How do we write this as an exponential? B to the x equals n. What's my base, b?
2,
It's the subscript 2. What's my n?
8,
8. And what's the exponent?
X.
X. That's it. That's right. You just identify the parts and put it in the
Okay.
transformation. So you can do the transformation both ways. And the reason we do that is because sometimes it's helpful for us to do that. We'll be presented a problem as a log, and you're like, you know what? Let's see what this looks like as an exponential and see if I can solve it that way. Uh, so let's do this. Let's do this one again. Where's that? Okay. So I'm gonna this exact same one, log base 2 of 8. Now you can do this on your calculator, by the way. Wait, let me see. Hold on. There's a log on your calculator. If your scientific calculator, you'll see log. You may even see on the iPhone, it may actually say log with a little 10 underneath. You'll see this. You'll either see log or you'll see log with a base 10. Okay, one of those on your calculator. They mean the same thing. On the calculator, they mean the same thing. Your calculator cannot do this problem. Okay, not in its present form at least. Because the calculator, the log on the calculator is a log base 10, a log base 10. Here, our log is a base 2. It's different, much different. So the bases are different. So you can't use this one. So because you can't use the calculator for this one, this is where it's advantageous to turn it into the exponential. Why? Because we learned how to solve that one yesterday, didn't we? How do we solve this one? 2 to the x equals 8. Get the bases to be the same.
So it's not 2 to the 8 equals X?
Nope.
The last one you gave us is not that?
Nope. Why? Because I had this. Let's see if I can get it back. See, there it is.
Hold on, let me see.
If we give you something just like this generically, if you're given something log base 2 of 8, you sort of just say they're asking you, what is that? Okay. Oh, what does that equal? X. Unknown. Got to go figure it out. So We can write it as log base 2 of 8 equals x, or just simply say log base 2 of 8.
Okay.
That's the shorthand for the exponential. Funny enough, that's also a number. It does represent a number. So you'll see it in either form. And you should then say, oh, that equals x. Now I can convert it into I can use my conversion, my translation.
So does it always end up equaling a number?
I don't know about always. The attorney in me doesn't like to hear the word always.
Oh, I'm sorry.
But when you don't have any when you here, look, you don't have any variables. So this will reduce down to a number. There is a number associated with it. If you had a variable, I can't say the same thing. So let's
Okay.
do some more. Let's advance further, because then maybe it'll help answer the question. So here we go. Write the following logarithm in exponential form. So how would we write this in exponential form? What's the base? The little number. It's the subscript number. What's the exponent? The number on the other side of the equal sign. And what's the n number? In this case, it happens to be the variable v that we're using. So now do your translation. So, b to the x equals n. So this becomes what? 4.4 to the fourth equals v. There we go.
So can just because I'm writing it down, so the base is usually the number that is the number that is down at the bottom, the smaller number at the bottom,
The
correct?
subscript. The subscript.
Subscript is what it's
Mm-hmm.
called.
Mm-hmm.
Okay, and then the x is what it's equal to,
Equal to, right.
and then the number is going to be
Whatever is over that subscript. It's what you're taking the log of.
okay. All right, got it.
Okay. Let's see what else I got. Same thing, translation. So we'll move forward. Translation. Write it as an exponent. Same thing that we've been doing. So this is a translation too, but this time it says it's the same thing, but it's just a little different because we have our exponent is now a 3x. It's an expression. Okay. Still the same thing. Still the same thing. This is your b, this is your n, and this is your x, if you will, your exponent. So b to the x over n. So b of 3. Now the exponent in this case is 3x because that's the thing that we were equal to over here. So it's not always x. It's whatever is sitting, this x here represents what the exponential part is. What's going to be your exponent. That's why I use x, exponent. So it's unfortunate they use 3x. I wish they didn't, but they did it. So this is the answer for this one. 3 to the 3x equals 121. Okay, wonder why we're only on number 2. Oh, I see why now, because I keep hitting try similar. Same thing, so turn this one and write it as a logarithm. It's the same thing. What's your b, what's your x, and what's your n? So this is, as a logarithm, log base 7 of 343 equals 3. So log base 7 of 343 equals 3. It's just getting the parts of the log and the exponential. Okay, so skip it. Okay, so solve the following log equation using the calculator if you need. Now, you'll see here it says ln parentheses 6x plus 1 equals 5. This is a log. This one right here, the ln is a log. It is called the ln is called the natural log. This is a log with a base of e. That's what it formally represents. So, in other words, ln is the same thing as saying log base e. Log base e. That's just for general purposes, okay? You don't need to know that. If you look on your calculator, there is an ln. An ln. You can do some of this stuff. That's a log base e. Now, why do we do this? Well, so if this is a log base, okay, yeah, so that's why we need to know this. So if ln is log base e, we would rewrite this as log base e of 6x plus 1 equals 5. We would use our transformation now. This is the b, this is the x, and this part, this whole thing here, is the n. Use your transformation of b to the x equals n. So we get e to the 5th equals 6x plus 1. And now you solve for x. So you have to calculate e to the 5th power, however you do that on the calculator. So let's see. E to the 5th power. So it's 140. So we'll come over here. 148.413 equals 6x plus 1. And then, now keep solving for x. So minus 1 divided by 6. The answer is 24.57. 24.57 equals x. But that's what they want you to, that's the key here, is the ln means a log with base e. And then you use your translation to finish solving. Okay. So I have a meeting. I have a thing I have to tend to. But this is pretty much how it's going to operate from here forward on the rest of them too. You're using the translation. Log base b of n equals x translates to b to the x equals n. You know, it works both ways. That's what this lesson is all about. That's what this lesson is all about. So we'll kind of end it here. What I'm going to do tomorrow, tomorrow's our last sort of meeting together, is we're going to finish up logarithms. We're going to finish up the other lessons. We'll see how far we get. Maybe we don't get to the last one, and you know what? If we don't, I'm going to give you the credit. So don't you worry about that. So I'm not going to make it injurious to you, but we'll get as far as we can. But I do want to be sure that we do some review as well. So we did some function stuff the other day. What I'll probably will do is look at some more recent stuff, and I'll probably also look back at the equations of lines, maybe some factoring as well, you know, systems of equations, equations of lines, all that jazz that we did from, I think, test 3, I think, something like that. Test 3 and test 2 is kind of what I'm going to look at to create some problems. And we'll do that together so that we can kind of finish out with a little bit of review and prep work. So I'm going to probably make the final exam tonight so that I know what I'm going to ask, you know, for tomorrow. Anywho. Okay, so I'm going to get this loaded for you all tonight as well. There's some weird stuff, you know, it's different from what you'll be doing, but really just follow the pattern. This one here, this lesson 6.3 is all about the pattern. transforming an exponential to a log, and then transferring back from a log to an exponential. It's just all about the pattern. That's the key to it all. So I hope you found this helpful. We'll connect tomorrow, and come with your questions too. Tomorrow's probably going to be a good review session for us too. So don't hesitate. All right.
All right. Thank
Okay.
you.
All right. Hope you have a good night.
Thank you.